Thanks to Keo for the introduction. Hi, my name is Jane E., and I'm here to present my work joint with Ohad and Maneesh Agrawala on optimizing portrait lighting at capture time using a 360 camera as a light probe. Lighting is an important aspect of portrait photography. So here, the lighting style is called loop. It's characterized by the strong light on the right side of the face and the triangle on the left cheek. To create this look, photographers have to carefully set up the studio as shown in the top-down diagram to the left. So here we see the subject at the center, facing the camera at the bottom. The light source is precisely angled to the right side and slightly above the face to form the desired key triangle. And setting up each of these studio lighting styles usually takes professional photographers tens of minutes. Here's a more dramatic look called Badger. It's characterized by the shadow along the center line of the face, and this requires two lights placed behind the face. Portrait photographers have designed many such portrait lighting setups, and here's a poster showing a number of these. In a studio, because the photographer has full control of the lighting, many different looks are possible. However, most amateurs don't have access to a studio, and furthermore, don't even know about these different lighting options. So consider taking a portrait in a natural environment like this one. The photographer has much less control over the placement of lights. Can we still achieve these studio-like lighting styles without studio lights? In many such cases, you can still achieve a wide range of looks just by having the subject rotate to different angles in place. But how do you pick which one is best? Given photos at different orientations, let's say we want to achieve the loop lighting style. So we can pick the photo that most closely matches this target style. However, the process of capturing these photos of the subject rotating in place at every 5 degrees is quite tedious, making sure each photo is free of motion blur and that the subject is properly posing. It took us over half an hour to capture this set of portraits. So our goal was to make this process easier, to allow people to leverage the insight that reorienting a person can result in various lighting styles without having to go through the process of trying out every possible angle. So we built a prototype interactive capture time tool that would guide photographers through the steps of choosing an achievable lighting style and reorienting the subject to achieve their selected style. So now let's say we're using this tool to take a portrait. So our approach consists of these 3 steps. First, the photographer has to capture the environment map. So since we want to know the lighting in the environment relative to the subject's head, we want the 360 camera to be at the location where the subject is standing, well, will be standing. In order to capture differences in light intensities, we capture a high dynamic range image. So given this, our intensity values can be much greater than 1. So in the bright sun, we have a very high value, orders of magnitude greater than that in the shadow. In the next step, we allow users to choose a lighting style from a gallery of pre-designed options based on studio portrait setups. So one of the studio lighting styles in our system is loop. We built a virtual representation of this lighting style by placing a virtual light source relative to a generic 3D head model with a fixed frontal camera, generating this rendered result. We've similarly recreated other lighting styles for the tool, including Badger, left split, or silhouette. Let's say the user picks butterfly, so it's a relatively evenly lit lighting style. This takes us to the next step, where the tool will now guide us to properly reorient the subject in the scene in order to best capture the butterfly target. Here is the Reorientation Guidance screen. So it tells the photographer how to rotate to produce the desired lighting. It also shows the current camera view and the target view, which shows the background once we reach the target orientation. So our goal is to match the background of the current camera view to the target orientation. The photographer guides the subject to turn. As we get close to the right orientation, we can also turn on the alignment mode, which shows how well the 2 views are aligned. Once we're happy with the alignment, we take the photo, giving us the even lighting of the butterfly style. So in order to prototype this interaction, we use the many devices pictured here. But we envision that all of this would happen in a single device, such as a phone, with an embedded 360 camera. Therefore, it's critical that our computation be able to run efficiently on relatively low-powered devices. So before describing our algorithm, let's look at some related work. Many computational relighting methods exist, enabling users to take an existing portrait and adjust the lighting in post. So these examples take a target portrait or environment as input and output a relit image. We focus instead on directly capturing the desired lighting in the camera. So in the moment, photographers have much more control of the scene and can make adjustments based on what they see in the camera. Because we're not manipulating the image, it has the added benefit that it cannot introduce artifacts. Some capture time tools also exist for aiding users in producing good portrait lighting. Merman et al. Present a system that automatically finds surfaces to bounce flash off of to light portraits, and Lee and Vogel present a capture time tool that can guide users towards an evenly lit portrait at a fixed location. So these works focus on a scene with one main directional light source, and we account for all lighting in the scene to allow for more diversity and creativity in lighting styles. Our work is primarily inspired by photography books on portrait lighting. These books suggest that good portrait lighting is about the overall distribution of light and dark regions on the face, rather than the exact levels of brightness or darkness or other high-frequency details. And so the orientation of the face relative to the light has significantly more impact on lighting than individual differences in facial features and skin. This means we can model our portraits using a generic head and skin model. What I want to compute here is what this head looks like when it's lit by a given environment map. So for this environment, here's the rendering. We use a method in graphics known as precomputed radiance transfer, or PRT, where the rendering B is computed as a matrix vector product between the lighting L and the light transport matrix T. So we use PRT because it's an extremely fast and efficient method for simulating lighting on a generic scene, suitable for running on a cell phone. It turns out that a low-resolution environment map is enough to capture a reasonable representation of the lighting in the scene. But what is T? So the light transport matrix encodes the interaction between the light and the objects in the scene. In order to determine the contribution of the environment, we render the scene lighting up a single pixel at a time. So it took us 17.1 hours to compute all these physically based renders on our desktop. However, it's a pre-computed step, and so once it's pre-computed, it can be used for all scenes, and so we didn't take any measures to speed this process up. Now we know how to render an image given the lighting environment. Next, we want to know how similar is this lighting to the target studio lighting, so in this case, loop. Looking at lighting similarity, as we discussed before, the key is relative regions of light and dark. Thus, for a given studio lighting style, we need to transform it into a representation of its light and dark regions. So we generate this weighting function f of x, where for each pixel x, a positive value, or orange, means that you want more light, and a negative value, or blue, means you want less light. We compute this by taking a masked version of the studio lighting and subtracting the mean. So once we have our target represented as these regions of light and dark, we can just dot product this weighting function by our render to get a single number that tells us how well B matches this F, and therefore the corresponding studio lighting style. So this is our quality metric. As we saw before, B equals TL. So this can be computed directly using our light transport matrix and our environment map as well. So we've walked through how to compute the quality for a given environment. At this orientation, the quality metric for this target studio lighting is 289. We can then rotate the environment map to compute a new quality value. Notice that this rotation of the environment map is equivalent to rotating the subject. So for this target and environment, 23 degrees is the optimal orientation. So here our quality metric is maximized with a value of 332. For this scene, we also have the corresponding photos at these angles. So as we scrub through other rotations, notice how the light changes. At the lowest values, the light is on the other side of the face. So remember, the optimal orientation we found for right loop was at 23 degrees and had a quality value of 332. Looking more carefully at this loop result, we can see the characteristic key triangle both on the face and the renders on the right. Here is another loop result in a different environment. Again, you see the key triangle on the left subject's cheek. And here we show another result for the loop lighting style. This demonstrates the ability of our tool to handle nighttime scenes as well. Now, let's look at another studio lighting style, left rim, with a strong contour on the left side of the face. In this photo, notice the desired highlight on the contour of the face, characteristic of rim lighting. So we're also able to capture the rim along this subject's face in an indoor scene. Now let's look at another studio lighting style. Below is a style with the main light placed below the front of the face. Revisiting our original scene, if we try to capture this style, we'll notice the result looks oddly like butterfly, so the face is relatively evenly lit again. This is the closest match the algorithm can find in this environment, as there's no light from below. So in order to help people better select studio lightings, we have an additional feature in the interface that I'll now describe. So here is step 2 of our interface again, where we select the target lighting style. Notice that some of the styles are grayed out, including below, as well as right rim fill. Our tool can automatically gray out these styles once it's given an environment map that's captured in step 1. We have found in practice that this helps users avoid looks that are unattainable and is especially useful for amateurs. So we ran a user study to evaluate the usefulness of our tool and the quality of the resulting photos. We asked participants to capture 3 well-lit portraits. First, using no tool, then using a static reference image showing the studio lighting styles where they would manually reorient, and then finally using our tool. They found our tool significantly more useful than the other 2 methods and helped them generate better lit portraits as well. When comparing our tool against having to manually reorient, our amateur users also found that our tool significantly reduced cognitive load. So we've also recently started experimenting with working in more constrained environments. So in this environment, there's no way to achieve this target lighting style. But many of us carry around a cell phone, so we can treat this as an additional light source. And our system can tell you where to place it to better achieve this style. Here you can see the subject holding the light to the right side, around 96 degrees from the direction where she's facing. Here's the result with and without the additional light. The portrait on the left only lights one side of the face, and the final portrait with the additional light source to the right is able to capture the light on both sides with a shadow down the center, characteristic of Badger lighting. So our tool allowed people to explore a variety of lighting styles, trying them with the subject while situated in the environment. We introduced this capture time tool for portrait lighting and are interested in designing capture time interfaces for other aspects of photography. For example, how can we leverage what we've learned to help people better light other objects, such as food? Or how can we help people be more intentional about composition? Some post-processing computational techniques have already been introduced in products such as the portrait mode on the iPhone. However, these can introduce some artifacts. So in the image on the right, you can see how parts of the straw are incorrectly blurred out in post. We hope that others also consider the space of designing interfaces for guidance directly in the camera. Thanks for listening, and I'll take any questions now.
Yeah, do you have any questions? And so, sorry, next speaker, can you start setting up your computer? Okay.
Hi, Scott Clemmer from UC San Diego. I think your idea of using computational techniques to change the image that you capture is so fantastic. I feel like that's going to be the future in so many ways. One thing I was curious about is that as a future step, is that I think a lot of times people don't know the terms of art. Like certainly if I was going to take a picture of myself, I would have no idea even which of these I wanted. And so I wonder if you've thought about either having an interface that's like, ooh, that one, or just make me look good or make me look cool or moody or something that might be more in the user's language.
Yeah. That's definitely something I feel like, that's definitely something I'm interested in looking at. And with this tool specifically, we don't yet touch on that, but it does give you the option of many different lighting styles. Like the butterfly is something that's used in a lot of like fashion magazines for something that's more youthful and like bright. And then like badger is something that's more dramatic. And so, yeah, we haven't translated to these other terms. But definitely something I'm interested in the future, kind of not just with lighting, but other aspects of photography as well.
Is there any other question? Yeah, go back.
Hi, Suki from Samsung. Just a quick question on the standards of the studio lightings. You said that they were matched with the studio styles and the coordinates. How did you find the data of what the preference is and how are they validated?
Yeah. A lot of times I was looking at the high-level description of how the studio lighting, like the poster actually had its own descriptions. It didn't say exactly where to place the lights and stuff, but it describes how you want the face to look. And then other books also have their own descriptions. So they are all a little different, and I mostly was trying to place lights such that I could achieve kind of the relative light-dark distribution that I wanted. Hopefully that was
Okay. So let's thank the speaker and then